So let me show you as best I can. So here you might see, look at my learner home. So here I see an assignment, which is this quiz 1 on differentiation, composite, implicit, and inverse functions, quiz 1, due tomorrow, 1 p.m. So if I hit start, it would take me to that quiz. But if you just go to the name of the quiz, it will open it, but you will see up here, this is quiz 1 in unit 3. So you could either go back and it will see this is lesson 2, and it has a number of activities, and then lesson 1 and a number of activities. If you go to unit 3 here, so one level higher, and you will find here is quiz 1. So everything for quiz 1, it's from the beginning up to the quiz. These are the things that you would be expected to learn in order to write the quiz. Does that make sense? Yeah? Okay, you can help each other if you're not sure. So then quiz 2 is also assigned. So you would find here's quiz 2. That means everything between quiz 1. So starting here, implicit differentiation, differentiating inverse functions, differentiating inverse trigonometric functions, selecting procedures for calculating derivatives. This is a really interesting one. How do you, so you know these different rules now for derivatives. So what is your strategy? Given a function, how would you go about figuring out the process? And again, more now with using multiple rules together. And then comes quiz 2. So the material for quiz 2 is everything between quiz 1 and quiz 2. Right? So just to go over it again, if you open your home page, you'll see this is assigned. If you click start, it will take you to the quiz itself. But if you click on the name of the quiz here, it will take you to, but you can then go up to the unit and then find, okay, here's quiz 1. So these are the content that prepare me for quiz 1. If I'm assigned quiz 2, this is this one here. This is quiz 1, that's quiz 2. So these are the lessons that prepare me for quiz 2.
Where can we actually get the lessons? Because I'm confused. You see, yeah, it is very different as for and platform. Very different.
Okay. So does someone have theirs open that we can use it as an example? Do you have yours open? Okay. So you have your assignments. So let's take quiz 1. That's the first one here, due tomorrow at 1. So if I go to this, so it opens the actual assignment or quiz. If I,
The second one.
oh, if I go back, is there? Oh, okay. So here's how I would.
Let's say like taking for this one, not started yet, but yeah, it's not bringing the.
It doesn't have the. Oh,
Yeah.
that's your other thing.
Yeah.
Okay, so we need to find then intro to calculus, my courses. Where do I find the? Oh, so you've only got this my courses. Can we add?
That is how it is bringing or false.
Okay, so we need, so what I would suggest is find math, AP, college calculus. So let me go back. Under, where is it? Explore. So this was your home. Go to Explore, go to Math, and then find, where did it go? AP College Calculus BC. And is there a way to, so this is the whole course. So then from the name of the quiz, you will know that, the quiz is called Differentiation, Composite, Implicit, Inverse Function. So it's from this unit. So you go to that unit, and now you could scroll and see, okay, all of this, and then here comes quiz 1. So everything above quiz 1, this is what I need to work on. You could also add, there's a section on the home page for my courses. I thought it would automatically add the course, but maybe we have to manually add it. So let me see, I have the app as well, so let me try. So here we are. See, I've added a bunch of courses already. So under my courses, you have edit or add. Go to your home, right? The home, same one down there. Yeah, and then go down to my courses. It should be empty for you. Not my classes, my courses. You found it? Everybody found it? Okay. So does it say get started or add or? Okay, so tap on that. Get started. My courses. I can go, resume. I want to edit. So if you tap edit, and then we want to find, where's the personalize, see all the math, and you're going to find AP College Calculus BC, and select that one. Okay. So here, my mastery goals, class courses. You already have yours. Good. So you can always open this one or resume. That's the course itself. So now you're in Unit 3, but you can go to the overall course. You have it already, so you just hit resume. My classes, get started. Get started. Go to there. Yeah. That's the one that I'm pulling from. You have AP Calculus. Oh, no. Well, hold on. That's the 2017 edition. Make sure you have the same one we're using. This one. So these are the units. So you see the quiz is from this unit. So you open that unit, and these are the content. And then will come the quiz. You've already done it. So now you could go on to the next one, unless you want to redo it. Yeah? Charles, you good? Are you sorted? Do you have the differential calculus? No, not differential calculus. You want this calculus. You can keep the other one if you want, but this is AP College Calculus BC is the one we're using. That's the one where your assignments are coming from. Okay, so hopefully that's good for me to know that it takes a bit of explaining how to use this properly. All right. So having said that, so the way I've laid out the remaining quizzes, there are 2 tomorrow, but then there would be 1 every day from now until, or from Friday. Wait, tomorrow's Friday. Tomorrow's Thursday. Okay. So two on Thursday, then 1 on Friday, 1 on Saturday, 1 on Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Last one would be Saturday next week. And each one will open 2 days before it's due. So the one due on next Wednesday, you can start on Monday. The one due on Friday, you can start on Wednesday. So that way you have 2 days to do the quiz. So each quiz is just a little bit. It's not the whole unit, right? And I think this way of making so there's 2 days, so if you have a very busy day, you can't do anything, that's fine, but pretty much every day you should be doing a little bit. And that will help to maintain a pace, not to just leave everything for one day and have a big calculus day. Does that sound reasonable, or is that going to be overly... Sorry?
So it's like for tomorrow we have 2.
Tomorrow's an exception that you have 2. After that, it'll be just 1 a day. So let me find... There's the drafts. So I can schedule this, schedule. So I'm curious now, if you look at your assignments, does it show you upcoming assignments? Not currently active, but coming? I guess I could check myself too. 3, past, upcoming. It doesn't say, huh? Yeah, so the quizzes are only, I think, 5 to 7 questions each. Each quiz, I think, is 4, 5, 6, 7 questions, something like that, on that content. Have you done it already? My courses. So if you go to my class, here's my assignment. Those are, okay, so it only shows you the ones that are currently active, but I will tell you, starting tomorrow, you'll see a new one appear due Saturday. Then on Friday, you'll see a new one appear due Sunday. On Saturday, you'll see one appear due Monday. Every day you will see a new one due 2 days later.
The assignments on tomorrow, it's showing 100% here, and the other one as well for tomorrow, it's showing, it's saying try again 86%.
So you did this one and you got 100, so fine. Here you got 86. If you want to try it again, you can. If you're happy with 86, you can leave it. Yeah? So the way it works is until the due date, you can keep retaking the quiz to see if you get a better mark. Are they part of your class grade? Yes. Yes. All right. So, today we want to cover a few topics. The chain rule, implicit differentiation, and you know what, I should write them over here. The chain rule, implicit differentiation, And we'll do, let me double check here. I think those you can just follow the lessons that are there. Not doing related rates, the meaning of derivatives. And then, so analyzing functions. So extrema, for example. And if we have time, it would be good to try a word problem. We might do the word problem after the chain rule. Actually, no, after analyzing functions. Yeah, okay. So, chain rule. Have you looked at this already, anyone? Huh? Quotient rule? Oh, we didn't do the quotient rule last week. Okay, so you want to do the quotient rule? The quotient rule is a kind of a special case of the product rule. And we can show how they are equivalent. So in the quotient rule, our question is, we are asking for the derivative of a function of x divided by another function of x. Right? And we're asking, what is this equal to? How do I take the derivative of the quotient of two functions? This f of x can be anything, this g of x can be anything. Right? And the answer is, I have to get it right, I know it's an f, but you may not recognize it as an f. F prime, I'm going to drop writing of x. You know that it's of x. Okay? So f prime times g minus f times g prime divided by g squared. That is the quotient rule. Now, we will use it. Let's use it a bit to see how it works. But I can show you first why it's also a special case, in a way, special case of the product rule. Actually, I can only show you that after we do the chain rule. So let's learn the quotient rule. And once we do the chain rule, we will see how the quotient rule is the same as the product rule. All right. So let's try doing this. So we want a ratio of two functions of x. So far, what we know are how to differentiate polynomials. Right? So let's write down a polynomial for f. Let's say x cubed minus x. This will be our f of x, divided by x cubed minus x, divided by minus x squared plus 2. In fact, I could even write it the other way. 2 minus x squared. Just looks a bit cleaner. Same thing, just written a different way. Right? So suppose you're given this. This is your function. Someone says, this is f of x. And they ask, what is f prime of x? That's the question. What is f prime of x if this is f? Notice, this f is not the same as this f. Right? This is f within the context of this. Here, f is the entire quotient. Okay? So, how would we approach this? We say, okay, anything above the line is considered this upper part there, and there's another function below in the denominator. Numerator and denominator. So what I do, I will need the derivative of the numerator, and then the function that is in the denominator, which I already have, so that's easy. I will need the function that is in the numerator, which I will already have, that's easy. And I will need the derivative of the denominator. So in order to be able to use this, we need these two derivatives. We need the derivative of the numerator and the derivative of the denominator. So let's do that. Okay? So x cubed minus x is our numerator. So let's ask, what is the derivative? D by dx of x cubed minus x. What is that? 3x squared minus 1. So we take the exponent, we multiply it in front, and we reduce the power by 1. Minus, bring the exponent in front, which is 1, and reduce the power by 1, which makes it x to the 0, which is 1. So 1 times 1, 1. Good. Now we do the same for the denominator, which is 2 minus x squared. What's that derivative? Negative 2x. How do we get negative 2x? So the 2
is constant, so constant is 0. Yes, so that power should go.
So minus 2 comes from that 2, and this remains 1. Very good. So we have our two derivatives. Yeah? Now we're ready to put all of this together. Okay. So I want f prime of x now. So f prime of x will be the numerator, the derivative of the numerator, which we said is this. Yeah? So 3x squared minus 1, in brackets, multiplied by g. What is g? G is the denominator. So times 2 minus x squared. Maybe to avoid confusion, let me just rename this. I wasn't thinking ahead. We'll call this function h. Yeah? I'm just relabeling. It doesn't change the problem, it's just giving it a different label, different name. So we're looking for h prime of x. So we have f prime, right? This is our f prime times g. Now we need minus f times g. So f is just this, right? This is our f, this is our g of x. That's our f of x. So minus f of x is x cubed minus x times g prime, which is this, right? So we could call this is g prime, this is f prime. So g prime is just minus 2x, and we have everything from the denominator. So this is f times g prime. Now we have to divide all of this by g squared. So g again is this, 2 minus x squared, and all of that squared. So this is g squared. Right? Now we can simplify. We can try to simplify, which is now just algebra. We're done with the calculus. Now we just have to simplify with some algebra. Do you want to do that, or shall we leave it here? Actually, we should, because we'll see what it becomes later. So let's simplify this. Start to simplify this.
Like that, that's the answer.
This is true, yes.
Like you can leave it like that, that's the answer. This is the answer.
Yeah. Just like if I say, here's a number, here's a number, and here is a number, and here is a number, and here is a number. All of these are the same thing, right? 1 plus 1 is the same as 3 minus 1, is the same as 2 times 1, is the same as 4 divided by 2, is the same as 2. They're all saying exactly the same thing. They're exactly equal, just written in different ways, right? So same idea. This is a true way of writing the answer, but it might not be the simplest, right? If you look at a number like this, it's much easier to see this than one of these. So usually, you want to simplify your answer. So let's try to do that. So we have we know we want to take usually the largest powers of x. I'm just checking if there's a step we could do. No, we won't be able to do. Okay. So let's collect the highest powers of x first. Actually, no, we could do that after. We'll just take them in sequence, right? 3x squared times 2, 6x squared. So we're going to get lots of terms. So let me start writing up here. 6x squared. And then this one with that one is? Minus 3x to the power 4. So we're finished with the 3x squared. Now we do minus 1 times 2. Minus 2. Minus 1 times minus x squared. Plus x squared. Notice that we're very careful to use the negative signs everywhere that they apply. So it's minus 1 times 2, minus 1 times minus x squared. Right? Okay, so we've done that one. Now we have minus. So we could put this in a bracket just to remember. Minus another bracket. X cubed times minus 2x.
2x cubed minus 2x.
Minus 2x cubed. No, actually not x cubed. X cubed times minus 2x is quad, 4. Right? The 3 and the 1 make 4. There's an x here. Then minus x times minus 2x.
Plus 2x squared.
Plus 2x squared. And that finishes the numerator, right? This is divided by, I want to be correct, so I put a hard bracket around all of it. Divided by 2 minus x squared squared. I'm not going to expand this yet because we might not have to. We'll see. Okay, that's this step. Now we do another. So now we can start to combine these terms. So what goes with what? We have x4 and x4. What do they add up to? We have a minus 3x to the 4th and minus 2x to the 4th.
Minus 5x.
Minus 5x 4th? Who thinks that's right? It's not. We have to be careful. This is minus. Here we have minus, minus. So this is now plus 2. So minus 3 plus 2 is just minus x to the 4th. Okay, what's the next biggest power? We don't have any x cubed, so we go x squared. We have an x squared here, here, and here. So what do they add up to? We have the 6 plus 1, 7, minus plus 2. So 7 minus 2 will be 5. So plus 5x squared. And then We don't have any single power of x, so then we have a constant, and the only constant is -2, so we have -2. Divided by 2 minus x squared squared. Is it possible to factor this? No. So we could leave it in this form. This is as simple as we can make it. You could expand this if you want, but this is, to me, this looks easier to read than an expanded one. Both would be true, correct? But I would end here and say this is the derivative of, let's remember, what are we doing? It's the derivative of h, the derivative of this whole ratio. Yeah? So that's how to use the quotient rule. Okay. I want to go to the chain rule, because with the chain rule, we will be able to derive this to see how do we get the quotient rule. Where does this come from? Okay. So hopefully I have enough room on the board to, I wonder, maybe I'll write it over here so we keep it for comparing later. Okay, so this was the derivative of x cubed minus x divided by 2 minus x squared d by dx of that. Okay, so now chain rule. The chain rule is something you really, you will want to practice a lot. It's not complicated, but it's subtle. So what does the chain rule say, and why do we need it? Okay. So far, we have learned a number of rules. We'll just write them down. So we have d by dx of a constant, say k. We know that's 0. If I have the derivative of x to a power n, if n is not 0, this is nx to the n minus 1, right? We know that the derivative of f plus or minus g is f prime plus or minus g prime. We know that the product rule, f times g, is f prime g plus fg prime. Now you might notice, this looks kind of similar to this. It's not the same. This one has a minus sign, but this looks similar to this.
So this can be plus.
The quotient rule is a minus. The product rule is a plus. Okay, but we will see how the product rule can give you this together with the chain rule. What are we missing? We're missing d by dx of a constant times a function of x. Function of x is a constant times the derivative of that function. Yeah? Or maybe to make it k times f of x is k times d by dx f of x. So the constant comes outside of the derivative. If it is multiplying something that is a function of x. If the constant is by itself, then the derivative is 0. But if the constant multiplies a function of x, then the constant just comes outside. So, okay, we can do these kinds of things. Now, what do I do with a function that looks like this. X plus 1 squared. It's not a very difficult function, right? It looks almost like x squared. I just have x plus 1 squared. How do I take the derivative of this now? Is the question. None of our rules tell us what to do with this. I know what to do with x squared, but this is not x squared. This is x plus 1 squared. And I can't just use the product or the sum rule because the sum is squared. I can't just ignore the squared. I can't just take the derivative of x plus the derivative of 1 and then square it. I have to do something, right? So this is where the chain rule comes in. What the chain rule says has to do with, so we need to remind ourselves about the composition of functions. To compose a function is to say, I have two functions, f and g. Okay? And the composition of functions, which is written f circle g, or f of g of x. Can you see okay with the tablet? It's you put one function inside the other function. The function g becomes the argument to the function f. Instead of f of x, it's f of g. And g is a function of x. Yeah? So let's see an example. Here. I could rewrite this. Again, let me call this h actually. So h is made up of two functions. It is a composition of functions. This is too big. It should be a bit smaller. One part of this function is x plus 1. And the other one is something squared. Yeah? To do this function, I do two things, one after the other. I do x plus 1, then I take that result, and then I square it. So to compare it to what I've done here, this would be my g, and this would be my f. The function g says take an x and add 1. The function f says take an x and square it. Take an input and square that. But in this case, the input is not x. The input is x plus 1. So in this example, we have f of g is g squared. I take this function and I square it. Right? So in other words, this is f of g of x. Have you seen composition of functions before? That looks like a no. Anyone? Has anyone seen composition of functions? F of g? Everybody's first time. In one sense, you could just learn the chain rule. I don't know that we need to go and do a lot of what is the composition of functions, but you need to recognize enough of, yeah, no, we probably need to do some more composition of functions. Okay, let's try to make some real world examples. What would be an example? Okay, we'll try this. May or may not work. We might come back to this example later. So composition of functions. So I want to know how much will it cost, right? I'm about to go on a trip. I'm going to go to Jinji. I need to put fuel in my car, right? And my question is, how much will that cost? The fuel to go to Mchinji, how much will it cost? How much will it cost to get fuel to go to, say, Jinji? Right? How would you answer this question? Forget about math, just what would you do? There's several ways you could do it. So I'm hoping we find one of the ways that will work for our examples. But for now, just how would you do it? How would we find out how much it will cost for the fuel to get to Jinji? Find out the distance, okay, step one. How much fuel it needs per kilometer, let's say, per distance. Okay, that's the fuel efficiency of the car. Yep, fuel economy. So if we know the distance, and we know how much fuel the car needs to go 100 kilometers, and Jinji is 150, then we can calculate how much fuel. And then the price per liter of fuel. Okay. What you have just, and to do that, so how far is it to Mchinji, roughly? How many kilometers? Huh? How many kilometers? I think it's more than 20. I mean, close to reality. 100? It takes like 2 hours to drive, so let's say 100, Jinji. Or 100? Okay, so let's say our distance, it depends how you're driving. It depends how fast you're driving. Okay, next we need to know how much fuel per kilometer, right? So we could call that efficiency C. So how many liters per kilometer? Typically it's like 10 liters per 100 kilometers, so 1 liter per 10 kilometers. 1 liter per 10 kilometers. Something like that. If it's not a very good car, it might be 8 kilometers or 6 kilometers. If it's a very good car, it might be 15 kilometers. And then we need the price. What's the price? Huh? Per liter. This is the price per liter. 2005. Huh? 2530 Malawian kwacha per liter. Okay, so we have the numbers we need. So now, in order to get the cost as a function of distance, that's really what we want. I mean, to go to Jinji or anywhere, I want how much will it cost for fuel to go to some distance, right? So we'll call this my function f of d is what I want. What I know is I can tell you, I don't know how to do this automatically, but I do know that if you tell me the distance, I can tell you how much fuel. So I could have a function that says, if you tell me the distance, it will be c times the distance. That will be the function. Right? You tell me how much distance, I multiply by my fuel per distance. That will tell me how much fuel you need. Right? Simple. Okay. And this will tell me the quantity of fuel. Let's call it Q. Right? Quantity of, actually maybe I'll put it here. Quantity of fuel as a function of distance. Now, if I know the quantity of fuel, I can find out the cost. I don't like that I used C. I'm going to change this to Y. Y is not a good one either. Let's call it, what? B. B is fine. We'll call this B times D. Because I want to use C for cost. Cost is C. That makes more sense. C of D is the cost. Cost C. So now C as a function of D, I don't know. I don't need to call it f of D anymore. This is what I want to find out. I don't know C as a function of D, but I can tell you the cost if you tell me the quantity of fuel. Right? If I tell you 8 liters, you can tell me the cost. If I tell you 25 liters, you can tell me the cost. Isn't it? So C is a function of quantity. In particular, it's the price times the quantity. Right? So now, I don't know C of D, but I know cost as a function of quantity, but I do know the quantity as a function of distance. So now I can compose the function. I can take my C of Q. C of Q is P times Q, but I know what Q is, so I'm going to replace Q by Q of D. That's C of Q. C of D will be P times Q of D, which is P times, now what is Q of D? B times D. P times B times D. I have put the function Q inside the function for the cost. Right? I didn't just put the number, I put the function in. So I don't even need to know if it's 100 kilometers. Now, you can ask me any distance. P and B are constants, so that's fine. So the final, now we have a function for cost as a function of distance. We take price times, not quantity, times fuel efficiency multiplied by distance. And then we could even put in the values. 2530 times 1 over 10 is 253, right? 2530 times, let me just write this, 1 over 10 liters per kilometer. So 1/10 times this is 253. And this unit times this unit per kilometer. So what happens, we have Malawian kwacha per liter times liter per kilometer. We take the units of P times the units of B. And the liters will cancel. So we're left with 253 Malawian kwacha per kilometer times the distance. So if you know your car, if you have you know how many liters it needs to go some distance, how many kilometers per liter, then you could make a new function that tells you what is the cost per distance. Very useful. Imagine you run a trucking company, or a logistics company, or a courier, or a taxi service, right? And people say, I need to go this distance, how much will it cost? Now you can very quickly say, the distance is 300 kilometers, 300 times this, that will be your fuel cost. we have composed the two functions. We took the function q and we put it inside the function of c. So that now c was not a function of d, it was a function of q. We knew the cost for a quantity of fuel, but if we know the fuel for a distance, then we can do, where is it? In essence, let me write it here. We can do c is a function of q, and q is a function of d, and therefore I have c as a function of d, which is this. So that's a very simple example, and because they're multiplied, it might be almost too simple. But you see how we took one function, we put it inside another function. So you already know how to compose functions. You just did it, right? Even if you didn't know what it was called, you know how to do this. So now we're just giving it a name, and we're going to use it. So let's think of another example that's a little bit more interesting. Any questions about this? Sorry, before we move on. Is it making sense? Do you think you can make a new example of a composition of functions? Think about it, and then talk with your neighbor. See if you can think of an example that involves the composition of functions, of two functions. Not multiplying. Putting one function inside another function. That's why this example was maybe too simple, because it looks like what you're doing is multiplying. You're not multiplying. You're using one function inside another function. As you're taking, let me put it like this. So we have the function q of d, and we had a function c of q, right? So here I have d is a quantity. It's an input number, this distance, right? What does q do? What does a function do? A function takes d and turns it into a number q. I have an input, it gives me an output. That's the job of the function. What does a function do? It takes an input, gives you an output, right? It takes d and makes it into a q. What does the function c do? It takes an input q and it gives you out a cost. It takes a quantity of fuel and turns it into a cost, right? The composition of functions is to say, I want this from this input. I want this input to give me an answer like that, right? Well, C doesn't do that. C goes from here from Q to C, not from D to C, right? So how do I get to C? I need something that takes me from D to Q, and then Q can take me to C. So now I'm going to compose Q and C. I'm going to start with Q of D, and then the way we write it is we wrap it inside. We take the result of this function, right? Q of D is the answer, the output. This output now becomes the input to this function. So Q of D is the output, but now I write it inside the bracket, so as the input of C. Okay? This is a composition of functions. And in fact, we can go even further. You could add another step. Something that takes the cost and calculates the tax. The tax on the cost is something, right? So then we could have, well, tax needs C as an input. So I have tax of C. Actually, I'm going to start writing it the other way. I have tax as a function of C. C is a function of Q. So I have C comes from Q. But then Q comes from D. So here I've composed three functions together. Q is the input to C. C is the input, D is the input to Q. Q is the input to C. C is the input to T. And when I put them all together, my composition of functions is T as a function of C, as a function of Q, as a function of D. So D will give me Q, Q will give me C, C will give me T. All right? Is that a, I think I get it, or is that a, I'm lost? Confused? No? It's hot, I know. I'm hot too. So, but that's the idea of composing functions, which you already, can you think now of an example of composing functions? And you can talk to your neighbors, try to think of, if I know this, I can calculate that. If I know that, then I can calculate something else. You guys think for a bit. I'm gonna pause this. One of these is a good one. Okay, cost, raw materials, labor output. So let's take them one at a time. And, okay, I'll keep that as an example maybe. It's okay, I got it. So, explain what you're thinking of there. Like these functions mean something from the, this is like an example from the real world, right? Or from your business class. Something. Output, what is output? What is the output? What's the thing being made? Yeah. Yeah, specific example. Pick a bread. Okay, so we have bread. And bread or mandazi? Mandazi. How do you like that? Or? Yes. Okay. So we'll call this an M. That's the out, or the output O. So mandazi, this is the number of mandazi. How many, right? That will be, O is going to be confusing. Can we call it Q, quantity? Yes. Okay, Q. Now, what do you need to make, how do you know how many mandazi will be made? The number of mandazi is a function of what? Okay, so it's a function of flour. Okay, we can call it F. Anything else? Are we doing multivariable functions? We can. Oil. You had raw material and labor. So let's just use two things. Let's say flour and labor, L. Have you learned multivariable functions? What? This is a two-variable function. A function will always give you one number out, one thing out. But a function can take one variable, or two, or three, or 10, or 100, right? What a function does is says, if you tell me this input or this and this input, or this inputs, I will give you an answer. That's a function. So a function can have, so far we've only worked with functions of one variable, f of x. X is one variable. But you can have a function of x and y, or x, y, and z, or 10 different variables. So here we have two variables, which we